Hello, my name is Thomas Kreutz and I'm from the Technical University of Darmstadt. I'm presenting our work on unsupervised 4D LiDAR moving object segmentation in stationary settings. Consider a scenario where roadside LiDAR is recording a traffic scene. In this scene, two moving objects are not able to see each other due to an occlusion. In this scenario, we might want to identify both moving objects from the LiDAR data to prevent a potential accident. In our work, we specifically address the problem of identifying moving objects from raw stationary LiDAR scenes. More specifically, we are given only raw stationary LiDAR point cloud videos without any annotations. Our goal is now to classify all points of these videos into being static or moving, without any annotations. This task can be called unsupervised 4D LiDAR moving object segmentation, and an example is shown below. Related work can be categorized into scene flow, map cleaning, dynamic occupancy grid mapping, and supervised end-to-end approaches. In contrast, we propose an unsupervised method based on representation learning that is focused especially on stationary LiDAR scenes. It can use more than 2 frames of history, and it does not depend on any annotations. Consider here the example of a moving object in the 2D grid on the top left. We assume motion to be expressed through specific occupancy change patterns within local spatio-temporal neighborhoods. We now want to model the change of occupancy over time of the green voxel. To this end, we record the occupancy of each voxel in its spatial-temporal neighborhood. The occupancy changes are first broken down into discrete time steps. Afterwards, we flatten the neighborhood into channels of a multivariate time series and collect the occupancy values. We repeat this for each time step and obtain a multivariate occupancy time series, in short MOTS, that models a voxel's change of occupancy over time. Using MOTS, our approach relaxes unsupervised moving object segmentation to a multivariate time series clustering problem. From a voxelized 4D grid, we compute MOTS for a voxel and encode it with a neural network to a new feature representation that includes now information about a specific occupancy change pattern. The encoder is trained as part of an autoencoder in a self-supervised manner. We repeat this process for each voxel in the scene and obtain a new feature representation for each voxel that we can use in the next step to segment motion. After computing the feature representations for each voxel, we can now cluster the voxel representations and obtain an unsupervised moving object segmentation of the LiDAR scene. We compare our approach against two recent state-of-the-art methods on stationary scenes from the Raw KITTI dataset. We find that our unsupervised approach is able to achieve performance that is comparable to that of supervised state-of-the-art methods when they are applied on stationary LiDAR scenes. In the qualitative comparison, our approach is able to achieve a segmentation that holds up with the supervised state-of-the-art with only minor differences. Here are some qualitative results on stationary KITTI scenes recorded with a Velodyne HDL64E sensor. We can clearly see that we can segment the moving objects. Furthermore, our approach is not only limited to a specific type of sensor, but it is also applicable to LiDAR sensors that are more sparse, like the Velodyne VLP16. To conclude, MOTS are an effective data representation to identify motion and stationary LiDAR point cloud videos. MOTS relaxes MOS to a multivariate time series clustering problem, and MOTS are applicable to different types of LiDAR sensors. Our code is available on GitHub, and thank you for your attention.